10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition. Liftoff of the Falcon 9 and Crew Dragon. Go NASA, go SpaceX, Godspeed, Bob and Doug.
America has launched. So rises a new era of American spaceflight, and with it the ambitions of a new generation continuing the dream. 20 seconds into flight, stage 1 propulsion is nominal.
T plus 30 seconds into this historic mission. Flying crew on board Dragon and Falcon 9, and look at them go!
Falcon power telemetry nominal.
Hola, ¿qué tal? ¿Cómo les va? Muy buenas tardes. Bienvenidos a otro episodio de Ecos de un Mundo Estrellado. La semana pasada estuvimos reflejando un impactante anuncio que hicieron desde Inglaterra, que fue el descubrimiento de bioseñales en la atmósfera venusina. Biofirmas, en realidad, un gas que se encontró, Fosfina, que podría estar indicando que es el subproducto del metabolismo de bacterias. Nadie asegura que haya vida todavía, sino que se trata de un gas muy específico que podría estar asociado a la vida. Bueno, y estuvimos hablando con Ximena Brevalla, una astrobióloga argentina, que nos dio su mirada, su perspectiva realmente importante sobre el tema. Les comenté antes de cerrar el programa que esto no se iba a agotar en un solo programa, me parece muy importante seguirlo. Creo que es uno de los anuncios o descubrimientos más importantes que se ha hecho en los últimos años, al menos en lo que hace la búsqueda de vida en el universo. Y bueno, la verdad que me puse a buscar a algunos de los responsables del trabajo, de la presentación del paper. Nunca creí que iba a tener la fortuna de hablar con una de las líderes de toda esta investigación, que es la doctora Sara Seager. Miren, la doctora Sara Seager es una eminencia realmente muy conocida en nuestra comunidad. Ella sobre todo se dedica al estudio de los exoplanetas, planetas que están muy lejos girando en torno a otras estrellas. Es una investigadora, doctora en física, astronomía, ingeniera aeroespacial del MIT, el Instituto de Tecnología de Massachusetts, que es una de las organizaciones más prestigiosas, ¿no? En lo que hace a la investigación científica en el mundo. Estas cosas que trae la pandemia, que realmente uno tiene la posibilidad de acceder a gente que de pronto, si no siempre está en algún avión o dando alguna conferencia. Así que realmente tengo el gusto de presentarles esta nota. La considero sinceramente, y miren que he hecho muchas, una de las notas que más voy a atesorar en mi vida, porque realmente busqué hacerla durante mucho tiempo. Sus respuestas son sencillas, cortas, espero que realmente la aprecien. Vamos a recordar nuestros auspiciantes y luego seguimos con el programa.
Estamos en emergencia sanitaria, pero en Inersa no nos detenemos. Trabajamos para brindarte un servicio eléctrico de calidad en cada rincón de nuestra provincia. Cuídate y cuida a tus seres queridos. Nosotros seguimos trabajando para garantizar la energía. Inersa, Gobierno de Entre Ríos.
Honorable Consejo Deliberante de Paraná, un espacio de pluralidad y voz ciudadana. Entérate de lo que pasa en tu ciudad ingresando a www.hcdparaná.gov.ar y seguinos por las redes sociales, Facebook y Twitter.
We are talking with Dr. Sara Seager. She is a professor of planetary science, physics, aerospace engineering, but you are an expert in exoplanets. It's really an honor to have you in this program. And thanks for accept this interview, Sara.
Thanks for having me.
Okay. So the big news is the detection of biosignatures in the atmosphere of Venus. I would like a definition of what implication this discovery has in the search for life outside the planet.
Outside the planet, you mean on other worlds?
Yes, outside. Yes, in other words.
Well, actually, this detection of phosphine, it's a very interesting lesson. Because although phosphine gas on Earth is only associated with life, on Venus, we're not sure what it is, actually. It could be some unknown chemistry. Or it could be a sign of life. We don't know. So to me, what it shows, it might not be the answer you're looking for, but it shows that it's going to be tough. The search for life on other worlds by way of biosignature gases. You know, we we'll have a lot of work to do once we find a suspicious gas.
How is possible that any life form survive in this such hostile environment that even melted spaceships? You remember the Venera landers?
Yes, the Venera landers were not, the surface of Venus is so hot. No life could survive on the surface. It's just simply too hot for complex molecules. But away from the surface, up above, high in the atmosphere, the atmosphere gets cooler and cooler away from the surface. And about 50 kilometers above the surface, the temperature is good for life. Not too hot, not too cold, but just right for life. But it's still an incredibly harsh environment, even when the temperature is the right temperature in the clouds. It's very acidic, very dry, and nobody knows how life could survive there.
Okay, so the phosphine fingerprints are very specific. There is no doubt that these signals comes from this molecule. Why they choose phosphine in first place? And is there other kind of molecule that can be so specific that you are considering?
Great question. The project lead, Professor Jane Greaves, purposely wanted to search for a sign of life on Venus. And she read the scientific literature looking for the perfect molecule. And she found these very obscure scientific papers one is from the 1990s, one is from the early 2000s, and they talk about phosphine as Earth as being only associated by life in oxygen-free environments. And phosphine also had a signature, like a fingerprint, if you will, at radio wavelengths. And she's an expert on radio astronomy. So she purposely went looking for phosphine. There are other gases produced by life, many, many gases. So we do have a list we could go look for on Venus or other planets. Some of these gases do also come out of volcanoes. Like we have methane, we have nitrous oxide, that's N2O. There's a long list of gases we could look for on Venus.
But not so specific to find life. I mean, methane, you can have methane from geological processes or causes.
Yes, you can. Mm-hmm. So the way that we have found it works is that many small molecules that are abundant, that are made by life, like methane, they're also made by geological processes. Because I like to say that nature has the same chemicals to work with that life does. However, there are a lot of other molecules that are longer and more complicated. There's one called dimethyl sulfide. It's a kind of a bigger molecule, and it's made by phytoplankton in Earth's oceans. And that one, I don't think there's a way that it's made other than life. But it's kind of niche, it's obscure, so it's not clear that life would make it elsewhere. So in addition to methane and gases like that, we have a longer list of more complicated molecules to look for.
And these gas, it's difficult to detect with our present instruments?
Probably. I don't think people have thought about that enough yet, but probably.
Okay. And astronomers could search for phosphine as a biosignature on much farther planets? It's easy, or the signal is too faint?
Right now, we don't have any way to study planets far away for biosignature gases. There might be one or two planets we could barely reach with the Hubble Space Telescope. We're all waiting for the James Webb Space Telescope to launch in about a year from now, hopefully. And we means hundreds of people in astronomy plan to use that to try to search for biosignatures. It would be very hard to search for phosphine gas using the James Webb Space Telescope. We'd have to be really lucky. There'd have to be a lot of phosphine in the exoplanet atmosphere, and we'd have to get a lot of telescope time to have any hope of detecting it.
Mm-hmm. So your team identified 16.8 billion features across the full spectrum to guarantee that it's really phosphine. So, I mean, you are really confident that it's phosphine. How is possible? It's really amazing. 16.8 billion, a lot of processing.
Yeah.
And you are confident, yes. So sorry, I interrupt you.
Phosphine because the signal was found with two different radio telescopes. with the James Clerk Maxwell Telescope in Hawaii, and also with the ALMA telescope, the ALMA array in Chile. So 2 different telescopes saw the same feature using different data analysis techniques. That's why we're confident there is a real signal. The team also searched through many different molecules just to make sure there's no contaminating molecule that might have the feature there. And we haven't found anything else. So yes, we're confident that we have detected phosphine.
And this is important because you also show that even in this condition, life maybe is possible. This is a hope to extend the habitable zone of other planets, of exoplanets.
Yes. Well, it's just so hard for our minds to accept that there could be life on Venus, even with the discovery of phosphine. Mm-hmm. We really don't understand how life could survive in the Venus atmosphere. But yes, it does help us expand our imaginations beyond planets just like Earth. And when we think of all the exoplanets out there, thousands of them and millions more waiting to be discovered, we're not sure what we'll find. So expanding our notion of what could be habitable is really important in the search for life.
Are you planning to confirm this detection with other telescopes, radio telescope? You can detect phosphine in infrared.
Yes.
Only. Radio waves or submillimeters?
Both. We can do both. We will try to get more ALMA time. Right now, all the telescopes have been shut down. Many telescopes have been shut down because of coronavirus concerns. Mm-hmm. But getting more radio telescope time to confirm is one step. Team members, people on our team and other people around the world are proposing to use ground-based telescopes in the infrared to look for phosphine at infrared wavelengths instead of radio. That will be tough because phosphine only has very weak features at infrared wavelengths. So those are the plans right now. There are also spacecraft going near Venus. There's one called Bepi Colombo. It's actually on its way to Mercury, and it's going to do a slingshot around Venus, a gravity assist. And so they're hoping to turn their cameras on. So there's a lot of things. I think a lot of people are going to work now to find a way to make more observations.
And ultraviolet, you remember that they found something that is absorbing ultraviolet radiation at the upper atmosphere of Venus. Hmm?
Right. There's more mysteries on Venus. And there's a pattern of ultraviolet absorption. People don't know what that is either. It's not phosphine, but people want to imagine there's a pigment. Like just to be fanciful, there's imaginations that there's some photosynthetic bacteria floating around in the atmosphere, and perhaps they're absorbing UV radiation with a kind of pigment.
I imagine, Sara, that from now on, other scientists will try to find non-biological or geological explanation, such as volcanism, for example. So this is how science works. Maybe yourself participate in this search. It's not funny, but... Okay.
Right. It's not funny. We'd like to have an explanation, and it would be sad but more reassuring if there is an abiotic way to make phosphine. And believe me, we have received over 100 comments from people in the community suggesting a chemical reaction. Most we've already considered. 1 or 2 of them we haven't thought about thoroughly yet. So we'll be working on it as well.
Yes, because you need to be very cautious. It's just we don't understand Venus as well as Mars, maybe. You agree with that?
Yeah, we have to be very cautious, for sure.
Those forms of life, according to what you have proposed, should exist within drops of sulfuric acid, can survive in this harsh environment?
Well, people have done experiments on materials that can and can't survive in sulfuric acid. Most things cannot survive. If you put like an ant, like an insect, or you drop DNA or sugar, sugar is part of DNA, they get killed or dissolve immediately, or to get destroyed immediately. So all of the building blocks of our life will not survive. It doesn't sound very promising. Mm-hmm. It doesn't, but some materials do actually. So sulfur, pure sulfur will survive. Wax made of hydrocarbons will survive. Graphite. And so there's a list of things that do survive. So it's a possibility that if there is life, it has somehow made a protective shell out of material that will protect it from the sulfuric acid. we need a lot more work, obviously, for people to dream up some kind of molecules that might be able to be used by life that could survive in sulfuric acid.
This discovery may stimulate missions to Venus. What kind of mission do you think will be ideal to confirm that there are bacteria in the Venus atmosphere? Maybe a balloon that float across the atmosphere?
Ideally, yes. Send a balloon to Venus, yes. And the Russians have already sent 2 balloons back in the 1980s. These balloons were coated with Teflon so that sulfuric acid droplets wouldn't puncture the balloon. And they floated around for about 2 days. We'd like to detect phosphine and other gases in the atmosphere. We'd like to detect complex molecules that couldn't exist without being produced by life. We'd like to bring a microscope and try to search for life itself. That will still be hard because there's a lot of aerosols and spherical droplets that will be hard to separate out from life, but that's the idea.
Maybe a mass spectrometer also?
Mass spectrometer to identify complex molecules.
But it's not too heavy for a balloon?
No, well, they make very miniature mass spectrometers these days. One we've looked into that is being designed for Mars weighs 7 kilograms.
Okay.
And we could imagine our balloon payload being maybe 20 kilograms for a small balloon. And so that would take up about half of our payload. So it's definitely, things are getting miniaturized these days.
Interesting. Let me ask you a more personal question. Maybe your feeling about this detection. This is something that you think it's finally the real thing, you know? In the past, we had several big announcements, like the Allen Hill meteorite or Vikings, inconclusive experiments. Are you really excited about this?
Well, I'm excited about it because I think it will help revive our interest in Venus and that it will help us get a mission to Venus to search for life and signs of life. You know, the funny thing about being a scientist is we get used to living with uncertainty. It's kind of frustrating in a way, but we don't have an answer and we don't jump to a conclusion one way or the other. So I'm excited because it's a mystery. I'm not excited because I think there's life there. So it's a kind of awkward way. It's hard to explain that, but I think you could help explain that to your viewers.
Maybe this is the reason why explore space. You never know what you can find. This is the joy of discovery.
Absolutely. And it turns out that Professor Jane Greaves, who started this whole thing, she completely did not expect to find phosphine. Even though she set out to look for it, it was almost like, it wasn't like a joke, but it was like, let's just try something crazy. Let us exercise the instrument and telescope like to its limit. Let's just do it.
Okay. In the past, we thought that we found life in the famous Martian meteorite, the Allen Hill meteorite. Now this is disputed, but at least this promoted the interest in Mars. Maybe this discovery impulse now to look at Venus. I heard James Bridenstine, the NASA administrator, say that it's time to think about Venus.
Yes, hopefully it will do that. We have a phrase in the US here, I'm not sure if you have something similar. We say, all ships rise with the rising tide. That means that if something good starts to happen, everyone can benefit. So if Venus gets promoted to being a body we should study, then everyone can hopefully get something out of it.
So they are considering 2 discovery missions, I think, among others. I think that there is a competition, but
right.
Maybe they need to be adapted to this new discovery to confirm phosphine or bacteria?
It would be wonderful if they could be adapted, but there's a big, we call it, say, inertia in the system. It might be hard for them to change something, although some of the instruments have to be fine-tuned for specific gases and compounds. So it's possible that out of the instrument suite they have, they can just make sure phosphine's on the list.
Okay. So we need now that an independent team with other equipment, maybe using their own processing methods and modeling, need to confirm this discovery. No? This is the process of science.
Right. It's the process of science. And hopefully people won't be too hasty. Hopefully they won't jump to conclusions with like a poorly thought out argument. Hopefully they'll give the same attention and care to detail that my team did.
You don't think that another molecule, or maybe a combination of several molecules, give us a signal that is very similar to phosphine?
No, the spectrum is pretty simple out at radio wavelengths. Molecules are rotating and they're interacting with radiation. And most of these rotational features are pretty well spread out. If you think about the infrared wavelengths instead of radio, it's crazy there. Molecules are vibrating and rotating all together. And sometimes they're vibrating in more than one way. And there the spectra is very complicated. Molecules overlap with each other, and it's very hard to disentangle things. But at radio wavelengths, it's a much more simple picture in terms of quantum mechanics and how molecules interact with light.
Which is the cycle of these bacteria in the atmosphere of Venus? What do you propose? Which is the dynamics?
Yes, well, what happened was we have been working on this phosphine result for a number of years. And my team at MIT, we've been involved for about 2 years. So my team actually pushed me to write a paper and to think about like a major hole in the concept of life in the atmosphere. Because we argue that life, just in the form of small bacteria, most likely has to live inside the droplets, where they'll be protected from the harsh outside environment. But the droplets grow over time. They collide and they grow. And as life is living and reproducing and metabolizing, eventually the droplets get massive enough so they start settling out of the atmosphere, like a slow and steady rain. So the whole was, how does life persist in the atmosphere for millions or billions of years? And the theory I came up with was that as the droplets fall out of the atmosphere to hotter and hotter temperatures, the liquid evaporates, leaving behind a spore-like particle. Now, without all the liquid, the particle is not massive enough to float downwards and become suspended in a layer. And there is a haze layer beneath the clouds that's not very well understood, and it's very stable and long-lived. And the idea is that this haze layer is populated with these hibernating spores that stay there until they can be updrafted back up, where they'll reach the cloud layer, attract liquid, become a droplet, and start the process over again. And the cycle continues.
The atmosphere of Venus is very complex. I heard Javier Peralta, you know him from Japanese Akatsuki orbiter.
Right.
He talked about a strange superwave feature in Venus, and he said that this affects the lower clouds of Venus, like the super rotation is there. I don't know if it's any relationship with your finding and this feature.
Yeah, not so much. I mean, the cycle has to be worked out in more detail. Right now, it's just like a one-dimensional idea, but it doesn't. I mean, the particles would get carried around with the superrotation as well, but at the same time, they will be falling out vertically if the particles get massive enough. But I fully agree with you and your colleagues. The Venus atmosphere is a crazy place with strong winds and a lot of things we still don't understand.
Now, it would be amazing to discover life in a place where we didn't expect it at all.
It certainly would be.
What goes wrong in the Venus atmosphere? In the past, I mean.
Well, we do think that Venus once started out like Earth, that it had a nice temperature at the surface and liquid water oceans, and that it could have been a great place to live. But Venus is close enough to the sun that we think it underwent an event that pushed it over the edge so that it became hotter and hotter and the water started evaporating. And water is our most powerful greenhouse gas. And so the more water in the atmosphere, the hotter the planet got. And more water evaporated and it got hotter and et cetera, until it ran away. We call it a runaway greenhouse. And that the oceans eventually all evaporated. And the water molecules got split up by ultraviolet radiation from the sun, and the hydrogen escaped to space, so eventually the water was lost completely. With all that water vapor in the water vapor got lost eventually, but all the carbon dioxide that was locked away in the water now became gas, making the atmosphere even more of a greenhouse. And so poor Venus ended up being so hot, way too hot for life at the surface.
Mm-hmm. I was thinking that maybe the discovery will push scientists to check all space missions data, maybe from Pioneer, Venera, Venus Express. What do you think? Maybe it's something that you miss, something that is hidden.
Yes, it might be worthwhile to go back and look at the data again. I didn't work on the data myself, but yeah, it might be surprising if people found something new. I think they looked at the data really carefully, but it's true. They could, who knows, they might find something.
Okay, I want to talk only a few minutes with you about exoplanets. You are an exoplanet hunter. Is your area one of your areas of expertise? Okay, go back to James Webb Telescope. NASA now is targeting October 2021 to launch the James Webb Telescope. I understand that there is a great hope of being able to solve the atmospheric composition of some exoplanets. What kind of gases could it detect, and what are the requirements for that these planets must have to achieve it? You know, how far, how big, rocky planets, big, giant gaseous planets.
Well, we have a lot of atmosphere observations with the Hubble Space Telescope and others of hot giant planets. And we expect that James Webb will do a fantastic job with those. They're bright, they're hot, they're big, and it's going to see so much detail, many different molecules we're expecting, like methane, carbon monoxide, water vapor. We're going to see a lot of other molecules, maybe ammonia. So
Oxygen?
we're really looking forward to seeing what it can do for giant planets.
Oxygen, Joe?
It'll be tough to see oxygen. We don't expect oxygen to exist unless it's produced by a geological process or life, because oxygen is very reactive. So we're not expecting to see that in giant planet atmospheres. If we do, it'll be completely crazy. We're also, with the James Webb, going to study a very mysterious class of planets called mini Neptunes. These are planets that are 2 to 3 times the size of Earth, and we don't really know what they're made of. They look like they're the most common type of planet in our galaxy, and we have nothing like it in the solar system. And those mini Neptunes, they're also bright enough and big enough for us to study in detail. And the third category is the rocky worlds. People really want to find life, but it's going to be hard with the James Webb because these rocky planets are very small and the atmospheres are always tiny. Plus, it turns out that an atmosphere made of carbon dioxide or nitrogen gas, they're very small atmospheres. They're tightly packed towards the planet. And that makes it even harder to study their atmospheres. Like in contrast, the mini Neptunes or the hot giant planets, they have hydrogen-dominated atmospheres. Hydrogen's a light gas, making the atmospheres puffy and easy to see. So people are kind of debating how well the James Webb can do for small rocky planets. But we're all going to work hard on the best targets to do our best to find signs of habitability or maybe even signs of life.
Is any space telescope in the foreseen future to study these rocky planets, the atmospheres?
Yes, well, NASA has studied space-based telescopes that would be very different from the James Webb. They would block out the starlight so we can search for planets and study their atmospheres directly. This is incredibly hard to do because the Earth is so faint compared to a star like the sun. But these telescopes now, they're being debated by a decadal committee that every 10 years meets in the United States of America. And they set the priorities for space science, at least astronomy space science, for the next decade. So we're keeping our fingers crossed that one of these space telescope concepts will get a high ranking from the community, and that we'll be able to start building one of those.
You know that besides being a journalist, I am an amateur astronomer. How we can contribute to the observation of exoplanets? What kind of telescope? Is there an observation campaign coordinated by an organization to be able to join? I don't know, some kind of photometry, for example?
That's a good question, and it's still tricky to contribute unless you have, sophisticated equipment, because the planets are so small. Even the giant planets, the signal they create with their star is pretty small, actually. If you could do 1% photometry, like if you can measure a drop in brightness of 1% with your telescope, and if you have a camera that has a good detector on it, you probably could help out. And I don't have a specific reference for you at this time, but I know that one way to help out is we're always looking for transits of exoplanets. And there are planets that are known to exist by radial velocity that might have very long orbits and very, very low transit probabilities. But people can predict when the transit might happen, if it's going to happen. And it's sort of a niche field, but the long period transiting planets are very rare and very special, and we'd like to have more of them. And somewhere I believe there is a website showing the times to observe.
Okay. Maybe you can send me some link to a web
Sure,
page.
I'll try to find it.
Okay, Sara, thank you very much. I really
Thank you.
appreciate your time with us.
My pleasure.
Thank you. Thank you. Thank
Bye.
you.
Estamos en emergencia sanitaria, pero en Inersa no nos detenemos. Trabajamos para brindarte un servicio eléctrico de calidad en cada rincón de nuestra provincia. Cuídate y cuida a tus seres queridos. Nosotros seguimos trabajando para garantizar la energía. Inersa, Gobierno de Entre Ríos.
Thanks for having me. My pleasure.
Thank you. Thank you. Thank
Bye.
you.
Muy bien, escuchábamos entonces a la doctora Sara Seager del afamado Instituto de Tecnología de Massachusetts. Espero que les haya gustado a ustedes la nota tanto como me gustó a mí hacerla, ¿no? Nada más, estamos cerrando el programa porque ya estamos pasaditos de tiempo. Muchas gracias como siempre por seguirnos y los invito, como lo hago siempre, a que se suscriban a nuestro canal en YouTube Ecos del Mundo Estrellado para ver programas pasados, muchos de ellos que no han perdido vigencia, y también para ver otros videos que generalmente subo a la red. Muchas gracias, hasta nuestro próximo programa.
That splashdown came right on time, 5:45 a.m. Pacific, 8:45